So hello friends, today I will teach you the pressure vessel topic, and I will prepare you in such a way that you will be able to answer any questions asked in the oral exam. Okay, so the topic name is pressure vessel. There are basically two types of pressure vessel. The first one is thin type pressure vessel, and second one is thick type pressure vessel. Okay, the pressure vessels in which the diameter by thickness ratio is greater than 20 are called thin pressure vessels, and if the diameter by thickness ratio is less than or equal to 20, the pressure vessel is called as thick pressure vessels. So the generally the spherical and cylindrical are the two shapes which are used extensively. So spherical pressure vessel and cylindrical pressure vessel, these are generally used. So now we will see the stresses which are coming in the cylindrical section. Firstly, we will study the thin cylinders, that is thin cylinders. Okay, so under the thin cylinders we have two shapes. The first one is the spherical, second is the cylindrical. Sorry, first one we will take first one as cylindrical and the second one as the spherical. Okay, so we will see the stresses which are coming in the pressure vessels due to the fluid present inside and outside of the pressure vessel. Okay, so stresses. Firstly, we will consider a cylindrical thin pressure vessel. Okay, consider cylindrical thin pressure vessel. So in this type of pressure vessel, there are three types of stresses which will be induced. The first one is the circumferential stress. The second one is the longitudinal stress, and the third one is the radial stress. Okay, though the first one, that is circumferential stress, also called as hoop stress. So when we call a cylinder, we will imagine a shape like this. Okay, so if we cut this cylinder along this section, so we will get a section like this. So if we cut the plane as shown in the figure, we will get a section like this. Okay, and this will be the direction of stress, that is, it will be along the circumference. The magnitude of this circumferential or hoop stress is PD by 4T. Here P is the pressure, D is the diameter, and T is the thickness of a vessel. Here one thing is to be noted. Here the pressure is taken as a local pressure. So what is this local pressure? Suppose if the pressure is varying along the length, that is it's varying along the length direction. So if you want to find suppose we want to find a pressure at this section, so we will take a pressure that is present at this point, and using that pressure we will calculate the magnitude of stress. So that the pressure at this cross section will be called as local pressure. Second one, if we cut the section like this, we will get a section like this, and the direction of the stress which will be like this. That is, this stress will be along the longitudinal direction. That is, the stress which comes in the length direction. It will be along the length, and its magnitude will be PD by 2T. This longitudinal stress comes only when the cylinder is fixed at the ends. That is, if the cylinder is fixed at the end, then only longitudinal stress will induce. So here the pressure should be taken as the end pressure. That is, the pressure which will come at this point should be taken as value of P, and this pressure will be of same magnitude throughout the length. This will be same here, same here, same here, same here. Okay, this will be PD by 2T. Now third one is the radial stress. Radial stress, we will take the same section as taken for the longitudinal section for finding longitudinal stress. This will be the direction of stress, that is from center to the circumference, and its magnitude will be same as that of the pressure. The magnitude of radial stress is small, so we will neglect it at some point or in some particular cases. Okay, so we have covered the stresses in the cylindrical section. Okay, so now we will cover the stresses in the spherical section. So for spherical section and thin pressure vessel. Okay, spherical thin pressure vessel. So here, as we know, the sphere is symmetrical, so the stresses along the that is the magnitude of circumferential stress and the longitudinal stress will be same, and this will be along the radial direction. So the magnitude of these both stresses will be PD by 4T. Okay, so both stresses have PD by 4T, PD by 4T and PD by 4T. Now we will see. So we have covered the thin cylinders. Now we will cover the thick cylinders. Okay, thick cylinder. So for thick cylinder we have two special cases. For thick cylinder, at case 1 we consider the vessel is subjected to only internal stress, and for another case we considered it is subjected to both internal as well as external pressure. Okay, so the first case is thin cylinder, which is we are considering only cylinder here, because in this because we are considering only thick cylinder because it's mostly it's used. Okay, now the first case is cylinder subjected to internal pressure plus external pressure. So there will be two types of stresses induced. The first one is the circumferential stress. The second one will be the radial stress. The magnitude of circumferential stress will be A minus B by R square and the radial force will be A plus B by R square. Okay, here A and B both are constants, and its magnitude will be, or formula to calculate will be PIDI square minus PODO square divided by D outer square minus D inner square, and formula for B is P outer minus P inner D inner D outer square by 4 D outer square minus D inner square. Okay. So this will be the case for a thick cylinder which is subjected to internal as well as external pressure. These are the formulas which will be required for oral exam, and now we will take a case when a thick cylinder is subjected to only internal pressure. That is, thick cylinder subjected to internal pressure only. So for that we don't need to remember the formulas. We just have to understand the concept here. So when a cylinder is subjected to only internal pressure and cylinder is a thick one, so that time this will be the section we have only internal pressure. So this will be as we have seen here, there will be only two types of forces, that is the circumferential stress and the radial stress. So the magnitude of radial stress at the outmost point, that is this point, will be zero, and as we move from outside to inside along the radiant direction, the magnitude of stress will increase. Okay, so this will be radial stress, and the magnitude of circumferential stress will be maximum at the inner side, and it will be minimum, not zero, it will be minimum, and it will increase when we move towards inside or towards the center. Okay, only this much we have to remember only. Now we will come to a design part. Okay, that is design of cylinder based on internal pressure. Okay, so to design a cylinder based on internal pressure, we have theories of failure. If a certain cylinder is failing in any one of theories of failure, then it will not be safe. So we have to check for each case, or so in our textbook there are basically 3 theories of failure. Basically there are 4 theories of failure can be used for design of pressure vessel. Okay, the first one is the maximum principal stress theory. I'll write small, max principal stress theory. The second one is the max principal strain theory. Third one is max shear stress theory, and fourth one it's max distortion theory, max distortion energy theory. Okay, so by using, so in this 4 theories of failure, we will calculate the thickness of cylinder which will be able to withstand the internal pressure. Okay, So there are 4 formulas which will be derived by these theories, and I think that formula is not required. It can be derived in the theory exam. It can be asked to derive in the theory exam. So just remember the thickness which will be calculated by maximum principal stress theory, and that thickness is the equation of that thickness is called as Lehm's equation, and this theory is used for brittle material. Then for the thickness equation which will be obtained by this maximum principal strain theory is called as Lagrange's equation or Brinell's equation. Brinell's equation. This Lagrange's equation is found out by assuming the ends are closed ends. Closed ends and Brinell's equation is derived assuming the ends are open ends. Cylinder ends are open, and both are used for ductile material only. Now that much is necessary. Now we will study the thick cylinder which is subjected to external pressure. Here we have seen only for internal pressure. Okay. So if we consider a thick cylinder subjected to external pressure, we will consider a thick cylinder. We have seen here that thin cylinder subjected to only internal pressure we have seen. Now we will see a thick cylinder which is subjected to external pressure. Okay. External pressure. So when a thick cylinder is subjected to external pressure, we will get a diagram like this. You just have to remember the diagram. The formulas for stresses are not required. Okay. So there will be 2 types of stresses. The first one is the radial stresses. Only the external stress is present, right? So the magnitude of radial stress at external point will be maximum, and it will be 0 at the center. But the magnitude of circumferential stresses, we have already seen that there are circumferential stress and radial stress. This will be the radial stress and this will be the circumferential stress. The magnitude of circumferential stress at inner radius will be maximum, and it will decrease as we move from center to circumference, but at the end it will not be a 0. Here it will not be a 0. The magnitude of stress will be 0, only the magnitude of radial stress will be 0, not a circumferential stress. Okay. So only this diagram you have to remember. Now we will see the pre-stressing of thick cylinders. Okay. Next topic is pre-stressing of thick cylinder. Pre-stressing of thick cylinder. So what is pre-stressing? We will cover that. Okay. So initially, suppose we have this cylinder and some gas is stored inside. So due to that gas, there will be pressure exerted on this cylinder. So initially there is some gas which will exert PI pressure. Due to that pressure, the hoop stress or circumferential stress will have maximum magnitude at inner radius. Okay. And minimum magnitude at outermost radius, as we have seen here. We can also see it here, like the maximum, this is the case of external pressure. So for internal pressure, this is the magnitude of circumferential stress is maximum at inside and minimum at outside. So this is what I have written. Same, the magnitude of stress is maximum at inside and minimum at outside. Okay, but we want to reduce, this will be the non-uniform stress distribution in the cylinder. Due to this, non-uniform stress distribution will be there. At inner side maximum magnitude and at circumference the magnitude will be less. Thus this will be the non-uniform stress distribution. So to make this non-uniform stress distribution into a uniform pressure distribution, we need to pre-stress the thick cylinders. Okay, so for that what will we do? Here the state is it will be the tension state at inner side initially, and it will be a state of compression, or it will be also tension, but it will be of lesser magnitude. So what we will do, we will induce a stress on a cylinder such that the outer surface will be under tensile loading, and the inner cylinder will be under compressive loading. So for that what will we do? We want, by pre-stressing, we try to achieve there will be a compressive stress at inner radius and tensile stress at outer radius. Okay, so how we can achieve this, or how to pre-stress a cylinder to achieve these results? So there are mainly three methods to pre-stress any component or pre-stress any cylinder. So first method is auto frittage. So what is this method? So in this method we are overloading a cylinder. In simple words, just remember, overloading cylinder before using it. Okay, overloading a cylinder before using it is called as auto frittage. So what we do in this method. So first we apply, suppose this is our cylinder. So firstly what we'll do, we will apply a pressure from inside. Okay, we will apply pressure from inside, and we will apply the magnitude of the pressure, magnitude of applied pressure will be such that the inner material will plastically deform, and the material which is present at outside, that is here, will deform elastically. Outer material will deform elastically. So when we remove that internal pressure, the inner material which is initially plastically deformed will compress, because the outer material which is elastically deformed initially will try to regain its original shape. Due to that, the outer surface will be under tension, and it will exert force on the inner side, that will, so that the inner part will undergo compression. So inner part will undergo compression. Okay. So the application of this method is interesting. It is used for a gun barrel. That is, we can also call it as, it's in the gun cylinder. Okay. Due to this method, we increase the capacity of cylinder. Okay. This is the first method. Now we will study the second method of pre-stressing. The second method is wire winding. Okay. It's very simple. We'll just, suppose this is our cylinder, we will just wind wire along the circumference. There is place available for winding that wire. Okay, due to the winding, the compression will be generated at inner side and tension will be present in the wire. Okay, this is very simple. So why we are doing this? We are doing this for pre-stressing of thick cylinder. What will happen due to pre-stressing? The stress distribution will be uniform, which was initially a non-uniform stress distribution. Okay, so these are the two methods. Now the third method is compound cylinder. Okay, so what we do in this method, it is also simple. Now suppose there are two cylinders, one cylinder and two cylinder. Okay, the bigger cylinder will be heated so that its the inner radius will get expanded, and we will fit this whole cylinder on this small cylinder. Okay, we will fit this big cylinder onto a small cylinder, and when the temperature, first stage is heating. Firstly, we will heat bigger cylinder and we will place it on smaller cylinder. When the temperature will reduce, we will get compression at inner radius of cylinder or at external radius of internal small cylinder, at inner radius of big cylinder, and tension at outer radius of big cylinder. Okay, now these are the three methods, and the stress distribution will be like this. Okay, so though is the thick cylinder and pressure is only from inside, we will get the zero pressure at here and maximum pressure. So this will be the pressure distribution inside, that is the radial pressure distribution, and at circumferential pressure distribution some magnitude increase, also increase. So this will be the pressure magnitude for circumferential cylinder. Okay, is the gasket joint in cylinder. Okay, gasket joint in cylinder. So here Suppose this is our cylinder. Okay, this will be the lower part of cylinder, and this will be the gasket. This will be the gasket, this will be the upper part, and this will be the lower part, and this is the bolt which we are using to tighten this. Okay, so initially when we for pre-stressing this gasket joint, we just initially tied the bolt, due to that a tension will be created in the bolt. Okay, when we tied this, there will be tension, created in the bolt. Okay, and due to initial tightening, there will be compressive force in the gasket. There will be compressive force in the gasket and flange. This is called as flange. There will be compressive stress in gasket and flange both. After when we apply a pressure, when we fill a gas inside the pressure vessel, there will be some amount of internal pressure. Okay, due to internal pressure, the bolt will be in tension, and the joints or the gasket and flange, this will be also in the tension. So look here, in pre-stressing condition, the gasket and flange is in compression condition, and after internal pressure application, or after applying internal pressure, the gasket is in the case of tension. So this kinds of balances out and reduces the amount of maximum pressure inside the cylinder. The cylinder will separate only when the force in connecting members will be less than 0. This is the condition for separation of joint. That is, joint will separate when this condition will be fulfilled. Next unit is design of pressure vessel. Okay, so first question is, what is unfired pressure vessel? So unfired pressure vessel is a pressure vessel which containing fluids having pressure greater than atmospheric pressure. Okay, what are the examples of unfired pressure vessel? The first is heat exchanger, and the second is evaporator. Okay, now the types of joints. Next question will be about types of joint. Types of welded joints. So just remember, there are 4 types of welded joints. First is double welded butt joint. Second is single welded butt joint, welded butt joint with backing plate, And the third one is single welded butt joint without backing plate. Okay. Fourth one is single full fillet lap joint. Okay, only remember this from this second point. Then we will see the categories of pressure vessel. Here remember there are mainly 4 categories, that is A, B, C and D. So these categories are made by the location of joint, means wherever the joint is present, the location at which the joint is present, according to that we will classify the joint as A, B, C or D. So the joint which is along longitudinal direction is A type. The circumferential joint is B type. The joint which is used for joining the flange or heads is type C, and the joint for a nozzle is type D. Okay, just now next. Now we will classify the pressure vessels, that is classification of pressure vessel. So the first type, so there are 3 types of, that there are 3 types of pressure vessels. The first is type 1, second type 2, third type 3. The first type is used to store toxic gases. Its temperature range should be minus the temperature of the gas, which should be gas or a liquid which should be stored in the cylinder, should be less than minus 20 degrees Celsius. For type 2, the temperature will be in the range of minus 20 to 0 degrees Celsius. And for type 3, the temperature will be between 0 degrees Celsius to 250 degrees Celsius. Okay. Now here all the 3 types. For the type 3rd, the pressure should be less than 3.5. Sorry, the pressure should be more than 3.5 and less than 17.5. Okay. Now all this type of pressure vessels can be joined by single welded butt joint or double welded butt joint. Single welded or double welded butt joint. Okay. Now next, so the important concept that you should remember is the corrosion allowance. Okay, so why to provide the corrosion allowance? They will ask you why you should provide a corrosion allowance while designing pressure vessel. So the corrosion allowance should be provided in the cylinder because of mainly 3 following reasons. The first one is the chemicals which are present in that we are going to store will react with the container and they will corrode some part of the pressure vessel. So we should add some thickness to the pressure vessel. That added thickness is called as corrosion allowance. So the reasons for corrosion allowance would be chemical or due to the moisture present in the atmosphere which will rust the cylinder or pressure vessel, or third reason is high temperature oxidation. If the stored liquid have high temperature, it will oxidize the pressure vessel. Okay. Okay. One thing is remaining. I will write it here. Extra, what is corrosion allowance? Extra thickness provided or extra thickness added to designed thickness to compensate thinning due to corrosion. Okay, so this is the meaning of corrosion allowance. So mostly we provide three type of corrosion allowances, that is 0 mm, 1.5 mm and 3 mm. Okay, 0 mm is provided when the fluid present in the pressure vessel is not a corrosive fluid. Okay, not corrosive fluid. If the fluid is little corrosive, or it's the corrosion ability of a fluid is not that much, so that time we will take 1.5 mm. And if the high corrosion ability of a fluid, if the corrosion ability of a fluid is high, then we will use 3 mm of corrosion allowance. High corrosive fluid. Okay. Now next, so now we will see the design procedure of pressure vessel. Okay, so what we have done, firstly we have assumed a vessel capacity, pressure vessel. Firstly we have assumed a pressure vessel capacity assumed. Okay, then using that we have calculated the length and thickness of vessel. After that we have found out the stresses induced in the pressure vessel. The stresses are of two types, the circumferential stresses and the longitudinal stress. For calculating longitudinal stress, we have considered three main factors, that is the pressure due to the stress which is generated due to the pressure of the gas present in the cylinder, that is internal pressure. Second is the weight of a pressure vessel, and third is the wind load. Okay, so by calculating the resultant longitudinal stress using this circumferential stress and resultant longitudinal stress, we have calculated the sigma resultant, that is resultant stress, by using distortion energy theory. Okay, then this is the design of pressure vessel. Then we have designed the openings. We have designed for 5 openings, that is nozzle, inlet nozzle, input, we take, let's say input nozzle, outlet nozzle, third is manhole, for manhole, 4 is for temperature measurement, and 5th is for pressure measurement. Okay, so we have also calculated the reinforcement material thickness is also calculated. During time of oral, you should know the length, the diameter, the material used for pressure vessel. Okay, these things you must know. Now we have also designed the gasket, the bolt, and the flange. Okay, these things we have done in the design of a pressure vessel. So for designing pressure vessel, we must know the type of enclosures. A teacher may ask question about this types of enclosure. There are basically two types. The first is flathead, and the second one is the formed head. Okay, so flathead is used for small diameter manhole covers. Okay, in flathead there is a stress concentration. The formed head is further divided into 5 parts. The first is plain formed head. The second one is torospecical head. Third is elliptical head, semi-elliptical head. And fourth one is hemispherical head. Fifth one is the conical head. This much you have to remember, and you must know the type of head which you have used in your project. Okay. So earlier we have seen that we have used the reinforcement pad in our design. Teacher will definitely ask you that what is a reinforcing pad. So its answer is and why it's used. So reinforcing pad is the extra material provided to remove a stress concentration or to neglect the effect of stress concentration. So the reason we are using reinforcing pad is due to a discontinuity in the vessel. At a particular point there is stress concentration. So to avoid the failure of material due to a stress concentration, a reinforced pad is provided. Okay, that is to avoid failure of pressure vessel due to stress concentration. Reinforcing pad is provided. Okay, this, and there are other some methods to avoid stress concentration. The one of the method we have already seen above. Okay, the first method to avoid stress concentration is to provide additional thickness near wall. Additional thickness near wall. Second, using, as already said, using reinforcing pad. Third one is by providing larger thickness to the wall. Providing larger thickness to wall. Okay. So now there is one method which is introduced, which is mentioned in the book, that is area for area method. Okay. So what is this? I will tell in a short manner. What is this method? I will tell in short manner. Okay. So when we provide a space for a opening, like when we provide a space for a nozzle or for manhole, at that time the material of the pressure vessel get removed. So due to this removed material, the strength of the material will reduce. So we will provide an extra material such that the induced stresses will be balanced, or induced stresses will be sustained by the pressure vessel. So area for area method is to calculate that area, that how much extra material we should provide, such that due to the removal of the material, the pressure vessel will not fail. So area removed to place nozzle is compensated by providing additional area. Okay. The strength which is lost due to the provision of nozzle is compensated by providing additional area, and this area is calculated by this area for area method. So for a shell, we can provide the area by using extra thickness. For a nozzle, we will provide extra area outside the vessel, or we can use the reinforcing pad. Okay. Now this much only we have to remember. Now the last topic is support for a pressure vessel. Okay. Support for pressure vessel. So in our syllabus there are mainly two types of pressure vessel. Okay. Sorry. In our syllabus there are two types of pressure vessel, that is vertical and horizontal. So we provide different types of support for different type of cylinder. For a vertical for vertical cylinder, we have namely two types of supports. The first one is the bracket support, which is also called as lug support, and the second one is the skirt support. Okay. The skirt support is mainly used when the height of a pressure vessel is more. When height of pressure vessel is more, and when height of pressure vessel is less, that time we used bracket or lug support. Okay. This skirt support is again subdivided into straight skirt support and angular skirt support. Okay, what is straight skirt? The skirt structure, the skirt which is having this type of structure, that this legs will be 90 degree to the ground. This type of support is called a straight support, and if the bottom legs of the support are at angle, right symbol angle, then that support is called as angular skirt support. Okay, so this is for a vertical cylinder. Now we will see the support which are provided for horizontal cylinder. For horizontal cylinder, we can provide a plate type support or ring type support. Okay, for plate type, the plate type support is provided for a small pressure vessel, for a small size pressure vessel, and ring type support is provided for large size pressure vessel. Okay, the plate type support looks like this. Okay, we are supporting only the bottom part. This type of support is called as plate support, and when we are supporting the whole structure like this, okay, when we are supporting the whole cylinder, that time the support is called as a ring type. So that's all. This much you have to remember in order to get very good marks in Viva for pressure vessel topic. Thank you.